Welcome, everyone. Thank you for coming to yet another day of the Diversity Intelligence Workshop. My name is John Hanke. I work here in the AI lab as a research software engineer. I also have been teaching data science for the last 5 or 6 years. I had a data science boot camp in the city a while ago, and I work with researchers in Natural Artificial Minds group to help understand language models, information theory, apply those kinds of techniques to understand what's going on inside of language models. Okay? And so, when I was told about this conference, I didn't get a lot of background, but I got a sense of what was generally being talked about, and I thought it might be kind of fun, depending on how people feel about it, and I want to be interactive, have kind of just a gentle introduction to large language models. So large language models, by definition, are large, and we'll talk about what large means, right? But that means they're kind of like complicated, and they're hard to understand. And so most of us use them as a black box. How many people have used language models? Okay, pretty much everybody. Okay, I'll do some questions, but they're kind of like, you use them, right? You don't make them. You just sort of like type into them. They say stuff back. You're like, cool, right? And so that's kind of the level I think most people interact with language models at. But they're machines. They're things that people put together. They work a certain way. They think a certain way, whatever that means. It depends how you personify models or things you interact with. And so what I thought I'd try to do today is give kind of a little bit of an overview of the main ideas about what's going on inside the box. Okay, so it's a peek under the hood. Okay, it's not a deep dive, but we'll do our best. But we'd love to have any questions or comments people have as we go along. Okay, that's kind of my goal for today. Also, I don't want to interrupt your lunch, and so I know of the two things, whoever's talking during lunch is much more important, right? So I feel like this is like a buffet dinner, right? I need to have jokes and things like that ready. I don't have any AI jokes, okay? But I will try to at least tell you a little bit about language models. Okay, cool. All right. So basically, text has been something that people have been trying to understand with computers for a long time, and AI is kind of like, in the last couple of years, really revolutionized the way that people interact with text and the computers interact with text. And so it's been kind of a very interesting journey. And so we'll talk a little bit about what are language models, how do you actually create them, what are the ideas and data that go into them, and then how do we sort of think about them as being a good model, right? Because there are lots of models out there. How do we kind of think about and evaluate them? This journey for most people started in fall of 2022, which is just not quite 4 years ago. But I don't know if people remember the world back then. At the time, I remember I was teaching a data science class, and ChatGPT had come out. We're like, oh, this is cool. And the last day of class, I had them write a poem about AI. Right? And we were all so impressed. Oh, I read a poem. It's amazing. It rhymes. It's reasonable. It's about the topic. But since then, it has just taken off and revolutionized every aspect of the things that we do. And so, with this sort of broad applicability in mind, I sort of want to talk a little bit about kind of what's going on. Okay, so the format for this is generally kind of please, it's a fun interactive session. So feel free to ask any questions you have. You have a question?
Do you want to go full screen with the slides?
Can I go full screen with the slides? All right, this is my first technical challenge.
It's that icon on the lower right.
Oh, an icon. Okay, I can't see this one. Did that do it?
Yep.
Is that better?
Yep.
Oh, okay, cool. Different from my view. Okay, great. So, so it's meant to be kind of a fun interactive session. If you have any questions, please feel free to raise your hand. Definitely want to address the things that you are interested in about language models. If you have phones, okay, turn them off. If you are busy or eating, totally cool too. And any questions are.
And if you may ask a question, tell them to use a microphone.
Oh, and if.
There are hand mics on the table, so if you could tell them that.
Okay, more technical details. There are hand mics on the tables, and so if you want to ask a question, you can use the mic. And if you don't use the mic, I'll repeat your question. Okay, so it's that's how we'll do it. Is that okay? Okay, great. Okay, cool. So pretty much everyone uses language models. How many people use language models every week? At least once a week. Okay, most people, I say about half. Okay, how many people use it every day? Okay, less. Okay, about maybe a third, a quarter. How many people use it for something important? Something like, yeah, I need to get this right. Okay, just a few hands. Okay, and so this kind of gives you sort of a sense of where we are kind of in the uptake of language models. They're cool, right? They can do stuff. They're interesting, but we don't really trust them yet. Okay, and so what I wanted to, one of the things, sort of my goals of this talk is to sort of give you sort of a sense of what you can trust and what you can't trust in terms of just how they work, right? So I'll sort of show you the details of how they work, and you can decide if this makes it sort of better or worse for you in terms of using language models. Yes, question?
Will we get these slides?
Will we get these slides? Yes. Yes, we'll distribute the slides afterwards. In some form, I'm not distributing them, but the important people will be. Yes. Okay. Other questions? Okay, great. Awesome. Okay, so here's a use of AI. Okay, I used it to generate the sort of sleeping cell phone icon in the previous slide. Okay, there are lots of different types of models out there in the world. Sometimes they're language models, which have to do with text. Sometimes they're image models. Those are usually called diffusion models. Those are a totally different type of thing. Nowadays, you see them bundled together with language models. Like you'll go to Gemini, you'll ask it to make some image. It'll say, oh, yes, thank you. And it'll use its own nano banana or whatever its internal model is. I think it's nano banana to sort of generate an image for you. It'll put it there in the prompt, okay, as kind of a response. That is not a language model. That's another model in the same interface that gets called as a tool as the language model decides, oh, I should call this thing to service your request. Okay? And so what we're going to talk about today is just the text part of language models. The other things are specialized models that get glommed together for commercial purposes. But if you want to download them for yourself, there are separate models for images, separate models for text, separate models for videos. Sora is one of the major video models that came out. I think it's being discontinued now. But there are lots of specialized models for lots of different things. Okay, so if you look, and we'll take a look about sort of where you find models in the wild, right? Where if you want to make models, find a model to do your favorite thing, X, Y, Z. Monitor traffic, label people's faces, make videos, whatever it is. There are plenty of models out there that do lots of things. Okay, but right now language models are all the rage, and so that's kind of why we're talking about this. But it's a larger ecosystem, much larger that all this fits into. Okay, cool. All right. What I want to talk about is sort of what are large language models, what is text, okay, because text it means something different to a model than it does to you. Have people heard of transformers? Have people heard of transformers? Okay, pretty much everyone have heard of transformers. Transformers are kind of the underlying architecture of the neural network in the model. Okay, so we'll talk a little bit about what that means and why it's a useful thing. And there's some ideas there. And then how do we understand models? Okay, what does it mean to understand a model? Okay, so the first thing to sort of understand is that to be able to have a model work with text is not so easy. Okay, so text is strings of things, and you want the computer to be able to sort of interpret what that means. Okay, and the way that we sort of think about text in a language model is actually not in terms of words the way we think of them. Okay, and so inside a language model, the way that text is processed is it's broken into chunks. Okay, and those chunks you could think of them as words. Okay, but the model doesn't know what any words mean. Okay, it doesn't. It starts out just saying, okay, it's like I was in Germany for a year. I took a German immersion class. Okay, what that meant was that they dropped me into a room of people speaking German, and I knew none, and I'm supposed to just learn it. Okay, I don't know if people have had this experience. It's very disorienting. It didn't actually work for me. It works for a lot of people, particularly younger people. It works better for. But that's kind of how language models start their life. Okay, they start their life by kind of not knowing anything about the things that they're seeing, but they learn by association. Okay? And this is maybe the first thing to know about language models. When you say dog, it doesn't think, oh, that thing I had as a kid, or that thing that runs around on four legs. It thinks dog is a word, right? And then from there, it has to build all associations through the text that it reads. Okay? And so this process of training a model, of getting it to understand or identify or associate different symbols with other symbols, or different words with other words. You might say different ideas with other ideas, because that's the way we think about things, is part of the training process of the model. Okay? But the model doesn't, when you tell it something and it gives you like a cool response, it is not thinking the same thing you were thinking. Okay? It's thinking something very, very different, okay? Even though it's been personified in really cool ways. Okay? So just a starting place. So what do models actually see? What do they think? Well, they start with text, and text is, for us, given as words, but for the model, it's given as tokens. Okay, and tokens are just a proxy for words. You could sort of think of them as words, but instead of saying that they're words, which we usually think of as spelled out with letters, each concept or each atomic unit of text is given a number. Okay, this is word 1, this is word 2, this is word 3, this is word 70,000, whatever it is. And it has a list of these things that it's allowed to say, and there's a finite list. Okay, it's a vocabulary that it's given. And it learns how to sort of put this together to say things that are meaningful to us, but it's always in terms of this basic vocabulary. How many went to the talk yesterday, Sarah Jane's talk? A lot of people. Okay, so people who were there, she was talking about how words are broken down into tokens. Tokens are roughly a half to 2/3 of a word, okay, roughly. Okay. There are different ways that models do this. Every model has its own way of tokenizing things or taking text and turning into labels from this fixed vocabulary. But that's sort of the first step. When you say something to a model, it instantly gets translated into what the model speaks, which is tokens. Okay. And so it's a string of tokens that go in. And what the model is roughly trying to do is to predict the next token. Okay. So here's kind of an example. So here's some text I might say. Oops. I have to learn how to do this. Princeton conferences rock, go Tigers. Okay, very pro-Princeton kind of message. And if I say that to my model, it would have to say, it would say Princeton. It'd be like, what is Princeton? And it translates Princeton into, oh, it's the first word in my vocabulary. And then conferences might be the 34th word in my vocabulary, and so on. And so what the model sees a priori is something that looks like this, tokenized text. And so each model has its own way of doing it, and I'll kind of give you kind of a demo as to what that looks like. But models will then be speaking back when they finish talking. They will also talk back in tokens, and those tokens get translated into words that we see, that we're used to. Okay, so there's this automatic translation layer that's kind of there. Okay, cool, awesome. Any questions? So we'll talk about what tokens are in a minute. I'm going to try an advanced move here. I'm going to try to change screens.
I did see a question.
Oh, we do a question.
Yeah, is the number of tokens at least as large as the language you're referencing? Like English is, I don't know, 100,000 words or so? Or...
Yeah, this is an interesting question. So it depends on the model, how they do it, what their tokenization scheme is, but generally no. Okay, no, and the reason is that there are lots of ways you could tokenize text. Okay, we'll talk about why we tokenize things a certain way in a minute, but like for instance, I mean, we all use letters to say English when we generally, right? There's 26 letters. There's some other stuff on the keyboard. You might be like, okay, there's maybe 100 different characters or 200 characters, or there's some ASCII encoding. You can sort of take letters and turn them into bytes, right? Maybe that should be my tokens, right? That's certainly a way to translate text into labels, okay? And that's one way to do it. But if you do that, then and so you can do that with a lot less tokens than the language size, right? The number of words. But to say any word, you have to say a lot of tokens. Okay, and so a token is kind of a bit of a trade-off between wanting to say things quickly, okay, and meaningfully. And so if you say something is a much bigger word as a token, it has more meaning, but I need more tokens to do it. Okay, and so keeping track of a lot of tokens is bad, but I also don't want to keep track of meaningless tokens because that's bad also. Okay, and so this is sort of a sweet spot that people come to, and it's roughly 50, 100,000 tokens per model. Okay, and we'll talk a little bit about how that's built up, but that's the idea. Okay, great question. Other questions? Okay, so again, trying kind of an advanced move here. How many people use ChatGPT as their model? Okay, how many people use a different model? What do other people use? Grok? Claude? Okay, so I think that the two major ones that people use nowadays, the most largest market share anyway, is ChatGPT and Claude. Okay, Gemini is all close behind. Grok is there. Microsoft has Copilot. There's a gazillion different models, and each model has its own choice that it's made about how to tokenize things. Okay, so what I thought I would do is just give you. So some of these are kind of like easy to sort of see online, and so I kind of have a demo here of a tokenizer. And I don't. Oh no, this is now. I can't do this in this mode. Okay, escape. Okay, cool. Awesome. So this is the tokenizer for ChatGPT, so I can make it bigger. Okay. So here I'm trying to tokenize the phrase, I am super excited about the Princeton Diversity Intelligences Workshop. Okay, so that's text. And if I say that to my model, it has to get translated into tokens. Okay. So what does it get translated into? It gets translated into this. Okay. So there are 14 tokens associated to this sentence. Okay. And there are so you count contractions, 1, 2, 3, 4, 5, 6, 7, 8 or 9 or 10 words. Okay, and so a token is roughly 2/3 of a word, roughly. Okay, and it's kind of non-trivial how this gets chopped up. I by itself, the letter I, capital I, is one token. Okay, apostrophe M is another token. Okay, meaning it's a contraction for I am. Right. Okay, so it's kind of simple meaning there. Super is one. -EXC is another token. Okay. And so you might say, well, why would that be a token? What does that mean? And it's a stem of something, and it has its own reasons for kind of making this as a token. Okay. And so it's kind of an optimization problem how to do this. The Princeton Diversity Intelligences gets broken up into 3 tokens, and then workshop is 1, and the exclamation point is another token. Okay. And that's 14. So when the model, when you say this to ChatGPT, it's thinking 14 tokens, and this is what they are, right? You can sort of see that's what ChatGPT sees. Okay. Okay, so that's kind of just sort of the first translation. Yes.
The token model is this different token models are the reason why we see different answers for the exact same question that we ask to different models?
No. No, the token model is not the reason that we have different answers when we ask the same question to different models. It's because they're different models. And so different models will have different ideas of how they associate information and say what the next words are. Okay, so maybe it's a good time to sort of mention, what do models do? What does a language model do? It is a very complicated, extremely expensive, very large machine that predicts the next token. All it's going to do is say, okay, well, if you tell me all these things, what's the token I should say after this that is most reasonable, okay, based on its training? Okay? And so all this huge infrastructure with all this compute and GPUs and cloud, and it's all just to predict the next token well. Okay? And predicting the next token is an interesting thing because if you can speak language well, right, and I say speak language well, I mean in the context of reproducing language someone else has said, who we think said it well, okay? If you can recreate that, then you have to understand enough about the world to be able to contextualize, get the grammar right, get the concept right. There's lots of different layers of understanding in that very simple problem of predicting the next token, okay? And that richness is what takes all of this space and compute and time and all that stuff. But at the level of a machine, it's just predicting another number from these 100,000 numbers or 50,000 numbers in our vocabulary, one after the other. And that's what you see in your chat session. Okay. Everyone cool with that?
Quick question.
Yes.
So
Wait.
it's already token 40,
Yes.
followed by token 2846.
Yes.
It's already tokenized and it's already represented by a numerical representation.
Yes.
Why are we still predicting though?
Why are we predicting? Well, right now, we're not, I'm just taking the text here. I'm super excited about the Intelligences Workshop and translating it into tokens. But what the model will do in a chat session, usually in a chat session, you say something and then it says something back, right? If you didn't say anything, it says anything back, it'd be kind of useless, right? And so what the model will do is say, okay, well, this is what you said. Now what will I say after that? It'll continue the conversation. So think of it as one conversation. Okay? And then when the model wants to stop talking, by the way, then it just says stop token. I put out the stop token and then my interface catches it and then it will wait for more input. Okay? And so not saying something is saying something, okay, in the language of tokens. It's an end token. Okay, cool. All right, any questions about that? Okay, awesome. If you're a Claude fan, you can see. Oh, question.
I
Sorry.
just have a follow-up question
Yes,
to
please.
that question. I just try feeding the same model with the same question, but different times, and I got the different answers. I like to know why. If I have the same input, like the should have the same token into the model, but I got totally different answers from. I'm using Claude now.
That's a great question. Okay, so so the question is, if you have the same input to the same model, shouldn't you get the same answers? And the answer is, strictly speaking, yes. But is it really the same model? Is it telling you deterministically exactly what the next thing is? And so the way models do is they really predict the next token. So if you download for yourself a local model, which has no randomization built into it, it will say exactly the same thing. But as a commercial product or as a sort of a feature of saying interesting things, okay, oftentimes what the model will do is it'll randomize. It'll say, well, you know, it's going to predict. It actually doesn't really just predict the next token. It predicts a distribution of all possible next tokens. Okay, predicts a most likely one and then a next most likely one after that with associated probabilities. So it gives you a distribution, and then you can for yourself say, well, do I want the most probable next token as my output, or maybe I'll just like take the top 5 and I'll just choose my favorite. Right? It's just sort of like roll the dice and sort of take that as the next one. And so that's called the top K selection process, and it's randomized. And so if there's any randomization at all, then you'll start to see that. And sometimes this is encaptured in a parameter called the temperature of the model. And so if the temperature is 0, then there's no randomization. But if the temperature is a little bit higher, then there's a little bit of stuff going on. Yeah, thank you. Great question. Other questions? Okay, cool. So just to show you, I'm really bad at this, sorry.
Just curious, so Claude's model and also ChatGPT, are they trained with similar data or different? That's like the underlying.
It's a great question.
Or is it just whatever's out there,
So the answer is we don't know, but almost certainly different data because there are two groups doing it sort of in secret, right? It's a commercial product. They're not telling us what data they're using or a lot about the model or its internal architecture or any of that stuff. They're just like, look, you want to buy something that predicts tokens? I predict tokens. And so that's kind of what happens. We'll talk a little about, there's one model I have some slides on, we'll see how the timing goes, which is an open source, completely open model. The different layers of openness that you can have, but this one is completely open in the sense that it tells you its training data, it tells you how it trained it, it tells you the different stages of the training, it tells you the parameters, and the timing, all of it. And so in that sense, and only for those models, do we have real information about what the training data is. Most models that are open source are open in the sense that they'll give you the model, which is it's a file of numbers, parameters for whatever it is, and you can download it and run it for yourself. But they won't tell you the magic, how it got there. It'll just be like, well, it's like congratulations, you've won a model, right? And so, yeah, you don't get a lot of introspection. Yeah.
Thank you.
Sure. All right, any other questions? Okay, cool. All right, so just to sort of give another example, this is the Claude tokenizer, and someone put up an app that sort of implements the Claude tokenizer. If you write some code, you can see all these tokenizations. They're sort of open in terms of what's going on, the translation. But this one, it uses 15 tokens, whereas over here, it used 14 tokens. Okay, and this doesn't quite show you exactly how it breaks the tokens down. It's also interesting, like when you upload an image to a model, it will also tokenize that. Okay, when it goes into the model, and so you can actually on this thing you can drop an image, drag and drop an image. It'll show you how big the image is when it gets tokenized. Okay, and how it thinks about that. That's kind of a compression thing. Okay, cool. All right, so back to our slides. This is the idea of tokenization. So this is, I think, the first thing I want to sort of mention to you. When a language model sees the world, it doesn't see the same world you see. Okay, and so the fact that you guys can talk to each other is really a miracle. Okay, and a lot of work goes into this process of making a model feel like a person. Okay, but they are not. Okay, they're different, but they're also very useful. Okay, let me try to do this again. Okay, great. Okay, so I gave you some the tokenizer examples. I put the links in the slide in case you want to sort of try it for yourself. Okay, offline. Wait for someone to take a picture. And so what I want to talk to you next is about what the model actually is. Okay, and so the model is it's called a neural network model. Okay, how many people have heard of neural network models before? Okay, how many people have used neural network models? They've made them themselves. Okay, very few. Okay, great. So this space in between is great because that's kind of what I want to talk about. So a neural network model it's an aggregate model. Okay, it is one simple model used many times in an interesting configuration. It's kind of like saying I have a house made of bricks, right? The neurons that make up the model are the bricks. Okay, and so you can put bricks together in lots of different ways, and that's what makes a neural network interesting. Not the bricks themselves, but the thing you build with it. Okay, the overall architecture. Okay. And so the architecture for neural network models, there's a little bit of math behind it, which I can explain. But the architecture generally it's called a feed-forward neural network. Okay. And so it's kind of like making a cake. Okay. You have a bottom layer of the cake, and then after that, you've got another layer on top, another on top of that. And then when you're done, the cake is done. Okay. And so information will flow only in one direction through these models. Okay, from the beginning to the end. Okay. There's some exceptions, but more or less. Okay. And there's an input where you sort of put your numbers in, okay? And there's an output where you sort of get numbers out, and these should sort of ultimately turn into tokens. You should want to put tokens in somehow and get tokens out, okay? And we'll talk about how that works. And in between, I only put one layer here. This is a deceptively simple picture, but there are actually lots of layers, okay? Lots, when I say lots, I mean lots and lots and lots of layers, okay? And so this becomes quite complicated. The reason a neural network is so interesting and so useful is both it's flexible in terms of its ability to adapt internally its architecture to understand things like all models do, but it's also flexible in terms of its ability to scale. You can make a neural network arbitrarily large. If you want to do something super complicated, just make a bigger network. If your other network didn't work, just make it even bigger and bigger and bigger. And this is the sort of scaling that language models have been able to take advantage of, is because these are sort of stackable, okay, like Legos, right? Then you can just keep, if you have enough Legos, you can make whatever you want, right? I mean, Lego fans there are, but okay, that's the idea. And so each of these dots here in our neural network, it does a very simple mathematical operation. So I just want to explain what that is. It's not a math talk, don't worry. Okay, but what it's going to do is it's going to take all of its so every dot here that's a blue dot will take all of the inputs from the previous layer. So you see all these dots here are pointing into this blue dot. There's an arrow 4 arrows going in, okay? And so it's going to take all the stuff that the layer before knew, whatever that means, okay? And it's going to take a weighted average of those things, okay? And do something a little funny to it, okay? And I say a little funny, I mean it's going to apply a function, okay? And that function is some function that we choose. It's not a linear function, okay? That's the important thing. So we can get out of like linear operations, but basically a weighted average is a linear operation, easy to do, right? If you use matrices in linear algebra, if you're a math person. And then I do this thing, apply an activation function, and then it becomes a little bit not linear, okay? And if you do this over and over and over again, you can actually approximate very, very complicated things. Okay? And there's a theorem that says you can approximate anything if you use enough neurons, any function, any outputs from the given inputs, whatever pattern it is, if you use enough neurons, you can capture it. Okay? And so this idea is like amazing for machine learning. It's like, well, you want to learn something? Well, use a neural network. It'll learn anything, right? How it learns it, how quickly it learns it, these are harder things, but it, in principle, in theory, can learn it. Okay? So that's kind of the idea behind this. Okay. Any questions? So as you go further in the neural network, in this case, I only have 2 layers, okay? But as I would call it going deeper in the neural network, meaning I've gone from further from the inputs, closer to the outputs. The things that the layer knows are much more complicated, okay? Because each layer is a slightly more complicated information than the previous one. Okay. So at the beginning, you might have general patterns, you know, try to find boundaries of things. If you like recognize the images, you might see like parts of an eye, like a curling pattern like this, or swirling that, or kind of a texture pattern. But as you start to sort of say, well, if I see this texture and this texture together, then that becomes more of an eyebrow, right? Then you start to sort of build more complicated patterns out of it. And that's kind of what the idea of this is doing as it goes deeper in the neural network, okay? And we'll see that language models are very deep, okay? And that's one of the interesting things about them. So the math of this is super simple. It takes a bunch of inputs over here, x1 through xn. It takes a weighted average of them. Okay, this is important because I want you to know that there are things that the model doesn't know that it tunes as it goes along. And one of the things is the weighting for all those inputs. How important is each input for what we get? Okay, and then there's an overall shift. It's called a bias. Okay, and so neurons are made from weights, which is these weightings of the inputs. Each neuron does this individually, okay, and then an overall bias. Okay, and so this neuron here has n inputs. Let's say there are 5 inputs, and so there would be 5 parameters, one number associated to each input as how much I weight it. Okay, and then there's an overall bias, which is a shift. And so this neuron with 5 inputs would have 6 parameters. And if you start doing this iteratively, it gets pretty complicated pretty quickly, and you get to billions of parameters very, very quickly. Okay, so it used to be, you know, tens of millions, hundreds of millions, then billions. Now it turns out, you know, you can run on your laptop maybe, you know, 7 billion parameter model, maybe a 30 billion parameter model. That's kind of a small large language model. And then the kind that you're used to, the ChatGPT and the Claudes, about 1 trillion parameters, on the order of 1 trillion, 1.5 trillion parameters. Okay? To give you sort of a sense of how big these numbers get, you've got to fit it all into a computer or several computers that coordinate to make it happen. But that's the scaling here, okay, that you can make these arbitrarily large. Okay, cool. All right. These are the kind of functions that people apply afterwards to the neural network model. They're really simple things, but all these things are not just a straight line. It's got a little curve to it, and so it's going to take the outputs of the model and it's going to adjust it in a way that will keep track of, will give it some ability to differentiate itself from just linear operations. Okay? And that's kind of the main point of this. One of the most popular things is ReLU. This is a very simple function to apply. This says that if the output of the neuron, so neurons, just to go back for a second, they take in a bunch of numbers, and they output one number. Okay, that's it. That's all a neuron does. Okay. And that number is applying this function to the weighted linear combination, the weighted average of these things that go in. Okay. And so the function you apply is often something like this. And so this is something that gives you the same output when it's positive and gets rid of all negative numbers, makes them all 0. Okay. This gives you something that goes up. This gives you something that's sort of like a swoosh. There's lots of different functions people choose, probably about 12 at most, but that's kind of the idea. Okay, so this is what a neuron is made of. So I'm telling you, I open the box. Okay, if you open the box, what do you look? You see a bunch of, you see a neural network with a bunch of neurons. And each neuron is just doing this. Okay, it's just doing this. Okay, cool. All right. So, okay, so that's kind of what a neural network is made of. And if you have a certain number of neurons, you can count how many parameters you'll get from it. as kind of a deterministically from the architecture of the inputs. Okay, and so the next question is, okay, great. So you got this neural network. How do I put text into it? Right? I have text or tokens. How do I get it into a neural network? I need to put it into these inputs here, these white dots on the left. How do I put numbers in? Okay, and this is a really interesting thing. This is one of the sort of most important ideas of text processing in neural networks. It came about around 2013. So there was this idea that you could use neural networks somehow to train models that have to do with text. Okay? And the idea was that you could train a model to predict words that were missing. Okay? And so you could take text and you could say, okay, well, I have like a sentence, and I'm going to take my model and I'm going to feed in the some number of words around that missing word, okay, maybe either before it or after it, something like that. Oh, excuse me. And then I'm going to have it predict the missing word. Okay, so it's kind of a word guessing game you could have the model do, and you would do this by just taking the inputs would be all the possible things of vocabulary. Okay, so each word would get its own sort of slot, and each would go in there, and that would be what you would predict. And so if you train a model to do this, to predict a missing word, okay, it turns out that the models can learn more than you expect them to. Okay? And this was the first hint that maybe you could do something with text that was really different from the usual sort of rule-based, grammar-based text analysis. Okay? And so this is from a paper which created an algorithm called word2vec. Okay? And the idea was if you train a neural network model, which is a very simple model, if you can sort of see it here, this takes n words, deletes the middle one, and wants to predict the middle word. Okay? And you can pick n to be whatever you want, maybe 5 or 7 or whatever it is, and it will just go through your text, shuttle through whatever text you have. It'll sort of take 5 words at a time, delete the middle one, try to predict that one from the 4 around it. Okay, 2 on each side. Okay, and it turns out it could do this reasonably well. Okay, and if you train this model to do this reasonably well, not great, okay, but definitely better than random. Okay, then if you look at the weights of this model, that's a bunch of numbers, and those numbers mean something about the words you fed in. And so I want to sort of give you just a sense of what this is, because this is a really important idea that's often overlooked when we talk about language models, but it's sort of the core of how we understand sort of a geometric idea of meaning. Okay? So what ends up happening in this paper is that you can take words and you can put them in space, okay? Like certain like stars in the sky, right? All your words go in different places, and where they are in space, from your perspective, tells you what they mean, something about what they mean, more than you would expect about what they mean. Okay? This is not a large language model. It's a very, very small, simple 2-layer neural network. Okay? There's nothing really going on. It's 1 layer in the middle, and just like the picture I drew before. And so using this, you can try to numerically, based on where things are in space, okay, answer questions about how similar 2 words are, or questions about analogies. This is to that as this is to blah. Okay? So how many people have heard of this before? Okay, these are called vector embeddings. Okay? I want to give sort of a quick example of this and go through. I think it's kind of fun to give you sort of a sense of what even this simple model can learn, and the language models really builds on top of that. Okay, this is one of the building blocks at the start of language models. Okay, so what you can do is you can try to predict words that are similar to other words. So this is kind of a simple example here. You can use GenSim, which is a library, to do natural language processing, which is what things with text and data is, if you try to understand text as data. And so it had built a model here. It's called the GLOVE model. And this is based on Twitter data. Okay, so there's a question before about what things are trained on. Okay, so these models are also trained on data that come in, text, strings of text you get from somewhere. And these were tweets. Okay, and it used tweets to do this. And so what you can do is, this is a 25-dimensional model, so it's a very small model compared to what we usually think about, which is hundreds or thousands of dimensions. Okay, and already, if you say, what is the closest word to the word Twitter? Okay, it knows the closest word in its experience to the word Twitter is Facebook, and then tweet, and then FB, and then Instagram, and then chat, in order of increasing distance. Okay. Now this is kind of surprising because we really didn't do anything in this model except train it to predict a missing word. Okay. But already, somehow, based on where things are in space, and this is really just looking at that place in space where Twitter is, okay, and it says, what's the closest point nearby, right, angularly? Okay. And it says, okay, Facebook, that's the next closest point. And that seems like a synonym, right? Facebook and Twitter are not completely interchangeable, but to first order, pretty much the same, right? They're both social media, they're both popular platforms, things like that. Okay. And so this was the first clue that something really interesting was going on, and people used this idea quite a bit. So I thought I would just give you kind of an idea of, from the Word2Vec paper, the kinds of things that this sort of very simple, this model here, can learn. Okay. You guys up to try some stuff? Because be Q&A now. All right. Okay. The last thing I want to do before I go into that is just tell you what I mean by nearby. When you, how people, I don't know if you can even see the stars anymore. How people look at the stars at night? It's so much light pollution. Okay. If I tell you there's a star here and a star here, do you know how far apart those stars are? Like if I say, oh, this is a star next to the moon, does that mean the star and the moon are close to each other? Not necessarily. But from my point of view, angularly, they're really close to, I look in sort of the same place. And when we talk about what we mean by close in these models, we mean the same type of thing. We look at the angular distance between the 2 points. They could be further or closer. It's not the Euclidean distance. So just so you know, sometimes people call that the cosine similarity, but it's really the angular distance. So it's something we're used to if we look at the sky. Okay. Okay. So for this paper, Word2Vec, this is the paper. It came out in 2013. Okay, it's called Efficient Estimation of Word Representations in a Vector Space. Okay, not a very sexy title. Okay, but it has a really cool idea. Okay, and so the idea is that you can try to find words that are similar to other words, and in particular, I think it's kind of surprising you can predict analogies. Okay, so even this simple model. When I was taking the SATs, we had analogies. Okay, this is so we're used to. I don't know if they have them anymore. But in this analogy, big is to biggest, as small as to smallest, right? Okay. And so the model will try to predict that. Okay. And it turns out that this kind of prediction, this analogy prediction, it's not just like a synonym or an antonym, right? It really has some sort of contextual meaning also, which is important to understand. And so this model can actually answer, the simple model can answer questions like this. Apparent is to apparently, as like is to likely. Walk is to walked, as swimming is to swam, right? Swam. So this is not just just to change the letters in something. It knows this is the right thing to be saying. Okay. Possible is to impossible, as ethical is to unethical, right? Okay. Mouse is to mice, as dollar is to dollars, right? Okay. So these are all different things that we kind of would do in normal speech, kind of grammatical type of things, right? Have to pluralization, modifying things, tense, things like that. Okay. So the model can do a reasonable job of predicting this. The simple model, again, this is not language models, we're building up to it, but already this representation of words knows quite a bit. Okay. And this is a very important point because language models leverage this as the first step. Okay. Harder one, Switzerland is to Swiss as Cambodia is to Cambodian, right? Here you're a member of that population. Okay, okay, cool. So these are syntactic type of things. Maybe more surprising, Athens is to Greece as Oslo is to, okay, right? Astana is to Kazakhstan as Harare is to, anybody? Zimbabwe. Okay. It knows this, okay. Okay. It's the capital. Okay. Chicago is to Illinois as Stockton is to Stockholm. Stockholm is Sweden. Stockton is a city in California. Okay? Okay, so it knows this relationship. And I'll show you how this does this with math. And it does it actually very simply. And that's kind of the surprising thing. All these things we think of as meaning, they're actually mathematical. Yeah, question?
How does it know it's just California? There might be many Stocktons.
That's right. That's right. So it's making a choice based on how it's puts words into space that the closest thing to what it thinks the answer is the word California. Okay. So this is not a
Why not
unique
New
thing.
Jersey? There's a Stockton, New Jersey.
Yeah, probably in its training data, it didn't hear about Stockton to New Jersey too much. Not too many tweets about Stockton, New Jersey. Right? Or not too much news about. So it's all about training data. All these associations are built from that. Yes.
Is embedding one value per word or it's multidimensional?
It is one point in space per word, but the space is multidimensional. So it's in this previous example, it's a 25-dimensional space. Every word gets 25 numbers, which is the coordinate in each of these 25 directions that puts it in 25-dimensional space. Okay. Yes. Yeah. Oh, sorry, over there. Yes.
What's the similarities or differences between an embedding and a token?
Yes. So an embedding, in this case, I'm embedding a word into space. And so embedding is where I take that word, which I'll call a label, or you could think of it as a token if you want, if I'm tokenizing by words, okay, and putting it somewhere in space. Tokens are just the way I translate words into that fixed vocabulary. And so for this part of the talk, we should think about words as tokens. But for language models, tokens are smaller.
So the number that represents a token represents a word, and the number that represents an embedding is where that word is.
Yes, so the question is, so the comment was, so a number that represents an embedding is where that word goes, but a number that represents a token is just that word. Yes, absolutely, yep. So there's numbers and there's vectors, maybe a better way to say it. So a vector is a list of numbers which talk about someplace in space. Yeah, question over here.
Yeah, I guess I'm just wondering how it, I guess, compares between different relationships. For example, instead of Stockton, if it's Paris, if it's going to say Paris, Texas, or Paris, France.
What do people think? Would it say Paris, Texas, or Paris, France? France, because it's going to be much more popular in terms of the way it's being talked about in its training data. But if it turns out you're from Texas and you only talk about things in Texas, it'll say Paris, Texas. Okay, so again, it's all about how it's trained. Yeah, question.
So in these large models that you were speaking of, like upwards of 1 trillion parameters, is it correct to say that every word is represented by a 1 trillion dimensional vector?
No, but every token is represented by a fixed embedding vector that is associated to that model. And when we talk about the open source model, I'll talk about the purely open source, I'll show you exactly what that is. It's a 4,000 dimensional space in that case. So every token, all of the 100,000 tokens, each get their own 4,000 dimensional vector as part of the billions of parameters of the model. Yes. Yes. So that's why I want to talk about this as the first step, because there's a lot built into just this simple representation that it's not a very smart model, but the embedding does a lot of the work for you. Okay? And this is kind of one of the paradigm shifts that happened in text processing, is that you could think about meaning not just in terms of like, what are the parts of speech? What do I think about a word meaning? All right, it's got like different types, it's got different attributes, it's different parts of speech, it goes in sentences certain places, I use it with certain other words. No, now it's about where it is in space. Space encodes meaning, okay? And it does it really effectively. Okay? And so that's the basis of language models. Cool. Yeah, last question. Yeah.
I have a quick question. If a word is breaking down into two tokens, like intelligence, like
Yes.
breaking down into intelligence, but their embedding can mean different things. How the model is going to deal with that? So yeah.
Yeah. So the
Basically
answer.
my question.
So the question is, how if you have a word fragment, like you take intelligence, right? We had this word intelligence. We got broken up into two tokens. How does the model deal with that? Technically speaking, each token will get its own embedding, and the model will have to create through its neural network architecture the appropriate associations to put those things together to form the full word. Yeah, yeah. But the tokens get meaning in that case. Yeah. Great question. All right, so let me just move on because this is kind of fun. I don't have too many slides here, but I wanted to go through. Angola is to Kwanzaa as Iran is to Ramadan. Okay, it's a holiday. Kwanzaa is a holiday. Okay. Turns out that Kwanzaa is also a unit of currency in Angola. Okay. Kwanzaa with a capital K is the holiday. Yeah. Okay. And so, okay, so it knows this because it's been reading the news, right? That it's read the news and it understands that when you associate currency to certain localities, there's that thing. Okay. And last one, brother is to sister as grandson is to granddaughter, right? It's a gender change in a relationship. Okay. And so these are things that this very simple, not fancy neural network model can learn. Okay. And so once you start to see this, you start to understand that that these vector embeddings are extremely important. And so what the model will be doing, as the neural network model and the language model, as this is part of it, will be doing is constantly adjusting where these different words go in space to better reflect the text that it's taking in. Okay. And so I say this is the first main idea inside of natural language processing that really advanced the field, because now all of a sudden we're not needing to be linguists anymore, or master linguists, or people who really understand all the contexts of things. The model will learn that for itself, right? And so we have been relieved of a great burden in terms of doing something complicated. We just say, look, learn this way, and it does it. Okay? And this is part of the mystery when people say, how does a language model work, right? The answer is we don't know. Okay? in the sense that if you said, why is this word there, right? It gets adjusted there through a series of incremental steps to make its prediction problem better. Okay? But we do know it's there, and we know that it's doing this to make the prediction problem better, but we don't know why it's there, right? We have given up control of that, and the model sort of figures it out for itself. Okay. Cool. All right, so that's kind of the idea here. So the math behind this is kind of interesting. The way that you actually do this prediction, brother is to sister as grandson is to, I would say, granddaughter, right? How do we get the word granddaughter out of this spatial representation of things? Sister is a direction in space, and brother is another direction in space, okay, another point in space. Okay? And the relationship between brother and sister, intuitively, here's where you wave your hands and you say, this just works, and so it's amazing, is sister minus brother. If I want to know the relationship that takes brother to sister as a math thing, okay, as a meta math statement, I would take brother and then add the relationship sister minus brother, because that's what takes me from brother to sister, sister minus brother, the brothers cancel, and I end up with sister. Okay? And this is the level of mathematics that goes into this. And so you actually do this with vectors. You say, well, sister minus brother is a relationship. I want to apply that relationship to the starting point grandson. So I take the point grandson, and then I apply the relationship sister minus brother, and I should get granddaughter. Okay? I look for the closest word around that point in space in that direction, and it turns out that it's granddaughter much of the time. Okay? And so this is where you start to see meaning turn into math. Okay? And this is very, very useful because math is much easier to do than semantic meaning. Okay? And that's kind of, this is the main point. So I just want to explain these vector embeddings are a core building block of these language models as we start. Any questions?
So the output that we're looking for at the end is the meaning of the whole sentence. Is that right? Or the question with the answers to the question? I'm not sure what is the end result.
Yeah, so the end depends on the end of what. So in this case, I'm just trying to use math to predict an analogy. And it turns out that this formula down here, this one, does it. If I take sister minus brother plus grandson, I will get the thing that fills in the analogy of granddaughter. Okay?
Okay.
And the logic behind that is that there's a relationship vector, which is the difference where these things are, and there's a starting vector. And if you follow the start plus the relationship, it gives you the analogy.
If we use the couple slides back, I am something, right? And they divide it into 14 tokens.
Yes.
What's the end result? What's the output?
So that's a different thing. That's not just using this vector embedding. That's trying to predict the next token. Okay. So here I'm not really predicting the next token. It's not a language model. This is just showing you how cool it is to put words in space. If you put words in space in the right way, it knows stuff. That's kind of the upshot of this. And this is the kind of stuff it knows. And you know it knows it because I just did this math, and that's how I got this word granddaughter. I didn't do anything else. This is literally just math with these embedding vectors.
Okay.
Okay. So we'll come back to the language models in a minute.
Right.
Yeah.
Sure. Okay.
Yeah. Question.
Yeah, just so that I think I understand this, but maybe not. So what is a sister and a brother? It's an offspring to a parent. So, and what is a grandson? It's an offspring to a parent also.
Yes.
So does that mean that sister and granddaughter are on that same vector pointing in space that has the same angle?
Right. So you have a way that you're thinking about that relationship, right? What those words mean. You have a context that you're giving it, right? And so you have your own semantic, logical way of breaking that concept down.
So that vector represents offsprings then, basically.
So you could say this vector, so roughly synonyms should be roughly in the same point of the sky, right? And so you would expect things that are roughly, so if sister, if offspring, if you have like son and daughter, maybe those are all kind of like in the same area roughly. It depends on how strong the gender differentiation is relative to the offspring differentiation. But the idea is that synonyms should be roughly in the same area, and that this relationship should be roughly synonymous to granddaughter. So I look at that part of the sky from this math, the closest thing is often granddaughter. And so it respects this idea.
So that region of that hyperspace represents offspring, basically.
Yes. Yes, exactly. And there are lots of different directions. As your dimensions get bigger, you get a lot more directions, right? I mean, in 2 dimensions, you only have this. 3 dimensions, you get a lot more. 4 dimensions, you get that plus more over 3 dimensions, and we're going to like 4,000 dimensions for language models. Okay, and so there's a lot of ability to differentiate concepts spatially, angularly. Yeah, yeah, cool, great questions. All right, so this is just sort of maybe one of the main points. If you take away, things from it's so far, it's tokenization is important, right? Language models read tokens, and tokens get meaning through spatial embeddings. Okay, and so that's kind of what's going on as the building blocks. On top of that, we then do some cool things. Okay, so I'll go through these. You can go through more of these, but that's kind of the basic idea. Okay, do you want to take a break? It's 1 o'clock. Are we good to keep going, or yes? Okay, all right, let's forge ahead. Okay, so the last thing I want to talk about in terms of the architecture of these models is this thing called a transformer. Okay, and transformers, it's not just more than meets the eye. Okay, it's this particular neural network architecture. Okay, about how neurons are wired together. Okay, and it has this idea in it of attention. Okay, so I want to explain what attention is, because attention is the main idea that lets transformers perform so well. Okay, so whenever you have a word that comes in, okay, the word is given a location in space, okay, and then when it goes into one of these, so I guess let me sort of go back to this for a second. Look at this architecture here. So the idea of a transformer is that it has this idea of you put your input in, okay, and it gets embedded somewhere. Okay, so all of a sudden your text comes in, all your tokens, and they get turned into points in space. Okay, inside the model, it'll do stuff in space, and then at the end, it'll go back to tokens. Okay, so that's kind of the first thing. So we've gone from our first paradigm of tokens, and we've gone to space. So now we're in space. Okay, words are in space, concepts are in space, everything's a point in space being moved around. Okay, and then what the model is going to do for each token. So remember, our tokens are. Oh, can I go back to this? I can't go back so easily. So the tokens are a list of labels, right? A list of numbers. Okay, and so for each token, it's going to ask a question. It says, "You're a token. Okay, what kind of things do you care about? What is important to you to understand what you mean?" Okay, so let's say I have a car. Okay, cars have lots of attributes. Okay, cars have different sizes, they come from different places, they have different colors, some are faster or slower, some are older or younger, right? And so these are different things that if I say I have if I say, what's the price of a car? That's a pretty vague statement, okay? If I say, what's the price of a brand new Ferrari car? Then that's a very different statement, right? And so the meaning of the word car has been modified by words around it, okay, or by tokens around it. And the idea of attention, which is the thing that this says scale dot product attention, and I'll show you what that means in a minute, is that every word is now not going to mean something by itself, which is what happened when we started out. Everything went someplace in space, right? Cat is here, dog is here, sister is here, granddaughter is here, car is here. And I'm going to modify where things are. I'm going to jigger it in space, depending on what I see around me, okay? And this is the idea of attention. Each token would like a little bit of attention from all the other tokens. Or said differently, all the other tokens give a little bit of attention to each token around it. Okay? And so when you put in a bunch of tokens together, okay, a string of, a list of numbers, what it's going to do is it's going to say, okay, well, and each little part of the network is going to do this. This is called an attention head. This will happen many, many times in the network. Okay? It will say, okay, well, I care about the type of car. Okay, or I care about the part of speech, or I care about the whatever. And for that thing I care about that I'm specifically tuned to, which the model will train itself to do these things, what types of words, what other types of tokens will help to understand that idea for the token I just saw? So if I saw car might be like, I care about colors. And so it might be like, okay, colors are important. Okay, and then other tokens might be colors, and they might be in that color part of space. Okay, so the car will say, I care about colors, something over here. Other tokens will be like, have to do with colors? No, I'm over here, I'm over here, I'm over here. Oh, I have to do with the color. Okay, I'm over here. Things that are closer to the thing that this token cares about will modify car. So then car is going to get jiggered a little bit. Oh, I see blue. Okay, it's going to move it a little bit. Okay? And when you move something in space, you change its meaning, okay? Because space encodes meaning. And so what this attention idea does is it's going to, as we put all these tokens in, it's going to take what each of them meant before and move it a little bit, based on the other tokens around it. And this is how language models acquire a contextualized sense of meaning. Okay? Words mean something by themselves, but they also mean different things together. And so it's going to keep track of 3 different things. One is called a key. Okay, that's the K here. The K is, what is it that I care about as a token? Okay, each token keeps track of this. Each token keeps track of these types of things. What do I care about the most? Okay, every other token will say, here's a value. Here are the things I represent, right? Which another token might care about. And the third thing is, how do I adjust for that? Okay, and that's what the key value query do. Okay, these three different vectors, and these are vectors in space associated to every token at every head. Okay, and so the model by itself starts with the notion of spatial meaning, and then every little piece of the model is going to modify that meaning in its own custom way. Okay, little different sort of focus centers in the model. Does that make sense? Okay. So this idea of attention, it's a modified, it's a dynamic, learned notion of differentiated meaning. Okay? It's not just one thing or another. It's lots of different things all at once, all being applied at the same time to jigger around vectors in space so that they mean just the right thing. Okay? And this is what a transformer does. This is what the transformer architecture does. Okay? And so this multi-attention head, it does some math. Okay? The math has to do with vectors. Okay? So it's going to be a dot product, which says how close two vectors are, roughly. Okay? And then it's going to be a shift based on that dot product. Okay? And these multi-attention heads, which are blown up over here, maybe I have some other slides to sort of show you. I don't have them right here. I have them a little bit later. This multi-attention head is one little piece. You see it? It says masked multi-attention head here. See that? One little piece of this transformer architecture. Okay. So this operation of what do you mean, what do you mean, what do you mean, contextualizing is happening many times inside of the architecture model. Okay. After that, there's some learning stuff that goes on, where I do a feed-forward neural network. I'll show you that in a minute. But basically, it's just a bunch of layers of neural networks like we talked about before that we use to classify stuff. And these get repeated. And so the transformer architecture is roughly look for what other things give it more meaning in a certain sense, and then do some learning on that concept. Okay? Build some other concepts off of it. And then feed that into other things that adjust the meaning, and then learn something off of that. Okay? And that's what a transformer does. All of this happens in the same ambient space, okay, in that embedding space. So when you say, where does a transformer think? Okay? It thinks in the 4,000 dimensional embedding space that you start with, or the 50 dimensional, whatever your size of your model is, but let's say 4,000 dimensions. Okay, and that's kind of where it's constantly adjusting its thinking as it moves through this. And this this architecture here, if it's not complicated enough for you, okay, you then repeat it like 60 times. You stack it. Okay, and that will make an example of like we'll talk about open source model, which is 7 billion parameters. Which is not that big, and then you could even make it bigger. Okay? But roughly, this is the three things that are happening inside of a model. So there's tokenization, okay? There's embedding, and then there's differentiated meaning through this transformer network that kind of adjusts everything in its own custom way, depending on the idea that that little part of the network is associated to. Okay, so that's a lot to say. I hope this is still a gentle introduction to language models. Any questions? Sorry, what's the question?
What outputs shift?
What outputs?
The right-hand side of that diagram. Oh no,
This
diagram.
This side.
Yeah, this side, the left side.
The left side.
Yes, and then there's a one input embedding, and then one output embedding. What the output embedding doing?
Yeah, that's a good question. So as you're going through your model, what I said before was, so the question is, what are the output embeddings doing here? Okay, and the output embeddings are, so when you talk to a language model, it doesn't just say one token, right? It says, it just keeps going, right? And quite a bit. They're very verbose, okay? And so what is it going to do? It's going to predict one token at a time, okay? And so it's going to take all the things it's seen before, and it's going to output the next token after all this complicated stuff. Okay. And then it's going to say, okay, well, all of those outputs, the tokens I had input plus the other one now becomes a new input. And so that gets fed back into the model, and then I predict the next token. And I add it to the end, and I feed it in as a new input, which is now a little bit longer. And I just keep doing that to predict the next token, and that's what you read when you read the ChatGPT text, translated back into English. Yeah, great question. Other questions? Yeah, over there.
question is just, how did people come up with this? Like, was this more of a matter of trial and error, or was it based on some mathematical theorems?
Oh, absolutely. It's empirical. This whole area is, I mean, I don't develop these models, but from what I understand, talking to people, is very much empirical. Even the attention paper, that was empirical as well. It modified another idea before it. This is all built on the idea of things being spatially embedded for meaning, which is the Word2Vec paper I showed you before. And so really people are just trying a lot of things, trying to make things learn a little bit better. And they've been doing that for some time. So yeah, it's a great question. Like, how do people think of this stuff, right? But this idea of attention, it comes from a very natural idea, which is that if I tell you a sentence and I just tell you one word, it doesn't mean the same thing as if I tell you it in context. And so how do you capture context? And context is roughly, how do other things affect this? And well, how does it affect it depends on, well, what it means, but meaning happens in space, and so you want to somehow modify where things are in space based on the other things around it, and this is kind of a simple mechanism. There's a formula for it. It's a very simple formula. It's not right here, but basically it's just a dot product, and that gets normalized a little bit, and you multiply that to weight another vector to shift it. And so the math is super simple, but the meaning of it, right, the reason that it's a useful thing, takes a little bit of unpacking to do. Yeah, great question, yeah.
So this all works on the number of tokens you give it. What happens if I give it a huge amount of text? Does it break it apart into groups of tokens? And then how does it associate one to the other? Doesn't it get all confused?
Great question. So this is part of the wonder of these models, is that the models have a certain, because they're neural networks, okay, there's only a certain amount of stuff you can feed into it, okay? And like I showed you way back, I'm not going to go back to the slide, but there were a certain number of inputs, right? Those inputs is one per token, right? And there's a certain number of inputs my model has. My model's only so big.
And what is that?
Could be 100,000 to 1,000,000 tokens, right? And so when you're having a chat with ChatGPT, it is reading everything in the chat to predict the next token, and then all of that plus the next token to predict the next one.
So will I break ChatGPT if I give it a huge, textbook amount of tokens?
At some
Or
point,
does it cut it off at a certain point?
at some point, it will stop. So if you use Claude Code, for instance, it'll say it's called a context window. It's the maximum amount that it can take in one go. Okay, and once you reach the end of that, it can't keep taking it in. So what it'll do is it'll try to look back at all the stuff you do and summarize it. And then it'll be smaller, but roughly the same, but it's not the same, okay? And then it will allow it to continue. And this idea of being able to compact or summarize, which language models do very well, in useful ways is part of the science of how these products are developed. But yeah, there's a context length and no bigger. Exactly, every model has a fixed length, yeah.
My question is related to that point. So how does the model know when to stop in terms of responding? So you ask a question and then what is the right length, and then they stop adding knowledge or adding sort of sentences to their answer.
Right. So it's a great question. So I mentioned this a little bit before when we talked about tokenization, right? There is also, so there are certain control tokens, right? Which one of them is called stop, right? And so if a stop token comes out, it will, the interface will stop feeding it back in, and then it'll wait for you to put some things in. And so a language model has trained itself to stop at a certain point. Sometimes you might say not soon enough, okay? But certainly it does stop at a certain point. That's how it keeps control. Also, there are other tokens called thinking tokens. I know people have heard of thinking models, okay? And the idea is that the model wants to have an internal dialogue, but doesn't really want to share it with you. But it's helpful for it to kind of know some stuff, just think things like we think things through before we give a talk, right? Okay, we have some little notes you make or whatever, and then it will sort of just share the final output. And so it's not kind of all drivel or a lot of details that you don't want to see. And so those are called thinking models. It's also tokens for starting to think and ending to think, usually markdown type of tokens. Yeah, XML. Yeah, great question. Yeah.
Could you please repeat the three properties in the multi-head attention? K was key, and it's what you care about the most. What was V and Q?
So there's a key. So every token has a thing it cares about. And then there's also every token has a thing that it does, right? A thing that it knows, okay? And I might get the mixed up, but for the purpose of this talk, it doesn't really matter. So maybe it's the query and the key. The query is what it cares about. The key is what it knows, okay? And then the value is how much it adjusts based on that, okay? And so that's kind of the idea. And those are vectors in space, and every token has one of those vectors associated to it for each attention head. Yeah, and that makes the parameter count go up very quickly. Yeah.
So if you ask a question to ChatGPT and then come up with the answer the question to the end result, right? I understand the embedding vector the operation, but how does that reach to the endpoint of give you the whole bunch of the right answer? That part I'm not quite get it yet. Yeah.
Right. So this is another miracle. Okay. So I've told you kind of like what happens mechanistically in terms of the model, what it's thinking, what it sees, what its parameters are, things like that. But so we use these things and it comes with these incredible responses, right? Oftentimes very coherent, smooth, polished, seems to know things, right? Not always right, but certainly better than guessing. And so how does it do that? And the answer, one token at a time. It does that one token at a time. It doesn't think through, oh, here's the concept I want to explain. I'm going to explain that concept. Its next token is conditioned on all the tokens it's previously said. So if it knows the next thing, it's because in your question you have given it that type of context that it says, oh, I should answer this type of way, and it's biased to do that. But mechanistically, it is answering one token at a time, and it will continue until it hits a stop token. Why does that work well? Because it's trained to predict the next word based on all the previous words well. And so if it starts saying something, it's going to keep saying something that's sort of saying the same thing, right? Because that's kind of what it's trained to do. But it is kind of a miracle. I mean, I can't tell you that now we understand it. It's still amazing to people that it works so well, right? Just like the embeddings were amazing to people. Yeah.
So from your talk, which has been great so far, I get a better understanding of how this stuff kind of works. I certainly don't understand it fully. But one of the early problems have been this hallucination issue. And from what you've explained, it seems like an awfully hard problem to resolve, but it seems to have gotten better.
Yeah.
And do you have any insight on how they did that?
Training. Better training.
Better training.
Better training. All these models are only what they are trained to be. Okay? And so you can train a neural network model to be anything. You can train it to be rude, you can train it to be friendly, you can train it to be, continuing the sentence, you can train it to be whatever you want based on the feedback, because all it's doing is trying to do this, optimize this problem you've given it. Okay.
But it's training on the same data set. It goes out and gets all the information off the internet or whatever it does. When it does a new training, it's a different model.
Yes, but. So let me sort of just unpack it a little bit. And I'll talk about training data. We're a little bit low on time. We'll see how it goes. But the training data it doesn't go get things. People get things, and they put it in a file, and they say, read this. And they have to keep reading it over and over. And they have an evaluation metric about how good the next token is. And that continues to get better, called a loss. Okay, and we'll see some of this. I'm going to do a live neural network demo so you can see how things get trained. Okay, but it's going to continue to improve that loss and keep trying to rejigger it. And if it's wrong, it's going to figure out, well, how can I adjust all of these parameters I have, all 7 billion or 3 trillion or whatever it is, to adjust it a little bit better to make it a little bit better predicting than what it should have been. Okay, and it does this over and over and over again for weeks and months. Okay, at the speed of a computer. And so it's doing this sort of monumentally complicated thing with the very understandable task of trying to get better, right? And so if you say that's wrong, then, or if the answer isn't what it's supposed to be, then you can say, well, maybe it didn't read enough stuff about that kind of math. Let me put some more stuff about that in the training data set. Maybe it doesn't understand this topic very well. Let me augment the data set with more of that. But that's kind of the way people do it. They take a huge run of data and they say, well, that didn't work so well, let's change the data we put in. But roughly, it's a hands-off process. Afterwards, people can sort of post-train the model based on preferences, based on its ability to interact and answer questions as opposed to complete sentences. And so there's some post-training that goes on. But more or less, it's always a training problem. No one ever goes in and be like, you lied, let me delete the bad neuron there and do, people try to understand things that way, but it's not the way things work in real life. Yeah, hands off. Yeah, great question. Okay, other questions. Okay, last question, then we'll continue. Yeah.
You answered some of this in the last question, but I know the basic architecture and all of the academic references are kind of over a decade, a dozen years old, and so the architecture has been there. But in the last several years, in the last 2 years, really, we went from something ChatGPT which couldn't pass the Turing test, and you could barely trust it for a couple lines of script code, to something that like modern Claude, which writes fairly complex software and creates this pretty exemplary output. What accounts for this dramatic shift just within the last year to 2 years in change in models when a lot of this architecture has been the same and the available data for input, the internet's been there that you could always feed to it? Is it just that we've reached this point on the curve in the training models, or is it something that's drastically changed about how they train?
Well, it's hard to answer the question because they don't publish how they do it, right? And so these big shops, they don't explain. But the compute has gotten a lot better, and people learn lessons from training models, and then they try to train them better. And so I'd say it's just part of the iterative process. They have hundreds or thousands of researchers working on training a model. Gemini, I think, has several thousand people working just on Gemini, right? And so there's a lot of ideas that go into how to optimize things. A lot of it is performance and compute. It takes a lot of time to do this. If you can do it faster, then that makes everything better because then you can do more of it. But you still have a deadline to release by. So I'm not an expert at training models, but I'd say generally the process has roughly stayed the same in that sense. Some architecture changes slightly, but basically there's been more focus on how to be able to train with better data or use the data it has more effectively. And also compute scales extremely well. I mean, you see what NVIDIA is doing quite well, right? So. Okay, cool. Okay, so these are the main ideas I want to talk about. I thought maybe kind of useful just to point out that there's a lot of questions about training. So training is something I want to give you an example of, so you can sort of see training firsthand. Because training a neural network model is something that you won't believe it till you see it. Okay, and then when you do it, then you're like, gosh, that's weird. Okay, and that's kind of what this is doing at scale. Okay, and so I want to give an example of that, but there's a lot of uncertainty in this process, a lot of randomness, a lot of architecture choices, a lot of data choices, as we talked about in terms of the training data, and some choices about efficiency. But this is very much an art, not a science. People don't know how to do this perfectly. It does a lot of stuff on its own. Sometimes it gets caught in weird places, and so there's been different technical improvements to try to do it better, but I want to give you at least a core experience of this. So as a friendly introduction, I'm not going to talk about more theory now. I'm going to sort of make a model, and I want to sort of watch you, have you watch it evolve and see what it does, and then then we'll have a conversation about what it means to train a model. Is that fair? Okay, all right. I don't know how to undo, is this? Yes, okay, cool. All right. So here's a, Here's a neural network. Okay, can I make this bigger? I'm not sure. Yes. Okay, great. Here's a neural network. Okay, I don't know if I can't. Can I zoom in? Maybe I can't. How do I undo this? Maybe if I zoom in like this. I'm not sure the right way to do it. I make this bigger. Okay. Here's a neural network. Okay, and what this is going to try to do is it's going to classify points. Okay, so just to be clear, the picture here, there's some inputs. Okay, I'm going to start with points in the plane. Okay, points have an x and a y coordinate, or an x1 and an x2 coordinate in the language it's using here. Okay, so to describe a point, I give it two coordinates, two numbers. Okay, this is not a language model. This is just a neural network model, but I want you to see how it works. It's the same idea. Okay, and so these numbers go in. Okay, and you can see this little picture here that sort of says, if it's the number that goes in, more negative or more positive. More negative is orange, more positive is blue. Okay, and that's kind of the idea. So you can sort of see this is keeping track of the left and rightness of the point. This is keeping track of the up and downness of the point. Okay, make sense? Okay. And here's a bunch of points. Okay, these are a bunch of points in the plane, and depending on where the point is in the plane, it gets a color. Okay, sometimes it's blue, sometimes it's orange. Okay, and my job as a neural network is to predict the color of the point. You give me a location, what color should it be? Okay, that's what the model's supposed to do. You could make it a classification model as well, but let's do this for now. And so what we're going to do is we're going to try to just train the model. And the way we're going to train the model is these points are here, okay? And it's going to just start from some random place, okay? These are neurons, by the way. So there are 1, 2, 3, 4, 5, 6, 7 neurons in my architecture. Okay? At the very end, the output of this last neuron is going to be the number that says whether it's red or blue. Okay? Blue is going to be 1 or positive, and orange is going to be -1 or negative. Okay, and that's kind of my goal. I want to predict that at the end. Everyone cool with that? Okay, so right now, so it's kind of interesting also, this great visualization here. This is called TensorFlow Playground. I'll put a link as well in the slides. Okay, I encourage you to play with it afterwards if you want. It really gives you an idea of what's going on. Each of these neurons has an output, okay, so that output goes to different places. You can see each neuron in this layer, all 4 of them get fed into each of these 2 neurons here. Both of these get fed into the next layer, and so it's a feed-forward neural network. Okay, it continues to move forward, okay, to the output. And each neuron is going to understand a different thing. So you can see right now, the way this is randomly initialized somewhere, if I reload, oh, I reload, that should be weird, okay. There we go. See, it starts in different places. So I'm randomly initializing the network with different weights and biases, and it starts by predicting different things. And you can see over here what it's predicting when we just start, okay? It doesn't really know anything, it's just starts somewhere, okay? And I'm going to run this by pressing the play button, and it's going to try to learn based on adjusting whatever the output is on all these points to get better. Okay, so let me just do it now, and we can talk about what it's doing, but see that? All by itself. Do it again. Happened kind of fast. Okay. And so you see the network is adjusting itself, okay? By the way it's adjusting itself, it's feeding in all those points that we saw, all the ones we started with. And every time it feeds in a point, like it feeds in this orange point, and then it says, oh, you predicted blue here? No, it should be more orange. And then it adjusts all the weights, all of the parameters for these neurons, all of them, okay, to be able to try to differentiate a little bit better that that should be an orange point. Okay? And as it goes through the process, you can see it learns. The way we can measure this is there's a function of how bad it is. Okay, it's called the loss function. Okay, how much error we have, and over time the loss function goes down. And that's how we think about a neural network. It does something. I didn't control this. I didn't tell what to do. I just said press play. Adjust yourself is what I said. Okay, and it adjusted itself. And eventually I said, okay, that's good. We're done. Let's stop. Okay. And this is what people do when they train neural networks. Now, the interesting thing about this, when I do it over and over again, does it do the same thing? That time was a little different, right? It kind of made this plateau. It was kind of unclear what was going on. Okay, try it again. Okay, now it's got like this weird thing off to the side. Okay, then it learned. Okay, great. Oh, learned right away that time. Okay, do you see there's a lot of randomness to this? Okay, it just kind of happens and it gets better. We can tell it's getting better because this curve goes down, but it doesn't always get better the same way. Okay, it doesn't always get better quickly. Okay, sometimes it's like, I'm confused. Okay, and then it gets better. Okay? But in this case, because this is a fairly simple pattern, okay, it can learn relatively quickly. Okay? And if you look at the neurons, how complicated they are, these neurons just know, or these inputs, they just know the x and y coordinates. Okay? The next layer of neurons, you'll notice it predicts things to do with different slices, different half planes. Okay? Okay? But they're different half planes. Okay? Notice they're all different features. This is like a blue on the bottom. This is upper left is blue. This is lower left is blue. This is mostly left is blue, but kind of slanty. Okay? And by putting those together, the next layer over here can really learn the pattern of blue in the middle and orange on the outside. And the way it does that is because it takes these as kind of negative part of this, negative part of this, negative part of this, positive part of this, and it feeds in. And if you add these together, you sort of see it's kind of like blue on the upside, blue on the inside, blue on the inside, and then blue, and kind of you makes a blue box, right, in the middle. And that's kind of how it gets that blue center to what's going on. Does that make sense to people? And so as we go through the network, it's learning successively more interesting features based on the features from before. Okay? This is just a two-layer neural network, but it can get more complicated. Okay. So there's a lot of choices you can make in terms of doing this. You could try to do things, change the function that you apply to your neurons. Here I applied hyperbolic tangent, which is a nice swoosh. I could do something that would make it slower. Sigmoid is a more positive swoosh, but it's also kind of gentler. If I train with the sigmoid function, a little bit different. Slightly different network, but it took a while to learn, right? Not so fast. Do it again. Is it learning? I don't know. Maybe, I don't know. Okay, starting to feel better. Okay, better. Okay. And these are the kind of things that if you're training a neural network as a neural network engineer, you need to be able to make these choices effectively so it can train quickly, right? So you use as least amount of compute as possible. Okay? And at scale, this is a huge difference. So this is kind of one thing about neural networks I want to sort of show you. Another thing is that they're not always right, and sometimes they get a little confused. Here's a more complicated pattern, okay, which I'll try to train relatively quickly. with ReLU, okay? And I'm going to try to learn this, and you'll see some weird stuff happen. So this spiral here about what color things should be, everyone can sort of see the pattern, right? There's a blue spiral and an orange spiral, okay? But the neural network can only just do these slices, okay? And so we're going to try to train it, and we'll see what happens. It's going to try, and you can see the loss is going down. It's getting better. It's learning, okay? But at some point, it's kind of like, I don't have a lot of room left. And it keeps trying to like take little steps to make itself better. And you can see it starting to like jitter and fidget and like, I don't know what's going on. Maybe I should do something different. I'll try it again. Learn something, then it gets kind of stuck, right? And then when it gets stuck, it kind of doesn't know what to do because it keeps trying to adjust, but it doesn't have the freedom to really do it. Okay? Now it's hard to know exactly how big your network needs to be to learn something, and so you kind of have to make adjustments as you go along. So maybe like, oh, okay, well it's not really getting the spiral at all. You know, what am I doing? Here you start to see it get more jittery. You can make it more complicated. You can add more layers. You can add more nodes. You can make a bigger network. Okay? And you could try to train it maybe faster, make the step size bigger. Okay? And you start to see if you make the wrong choices, it can kind of train, but also kind of do kind of bumpy, right? So it's not like a smooth path to training. In this case, it kind of learned what was going on. I gave it enough room, but it's kind of a bumpy path. Try again. And each time I do it, it starts from a random place, okay? And you can see it's not always, okay, it was learned, but then it forgot. Okay? So neural networks, there's a lot of like choices to make it actually really work under the hood. Okay? And I just want to make this point. And so if you're good at this, if you have a lot of practical experience, you can try to get the choices right. Here, it looks like it's kind of jumping around too much. I should make the step size, the learning rate, a little bit lower. Okay, we'll try again. And then maybe it'll kind of learn more smoothly because it'll take smaller incremental improvements until it gets better. Okay? But this is kind of when you're sort of creating a neural network, creating a language model, which is, again, a very, very big neural network. It's trying to do something like this, reading all the text that you've fed it from the internet that you have in your training data. Right? And sometimes it gets stuck, and sometimes it learns something, and sometimes you're like, you know what, that's good enough. Right? And then you stop, and then you deploy it. Okay? And so people say, why do you get different answers from different models, or what is it doing, or why is it happening? It's doing this. I mean, something like this, a very big version of this is happening, and it's trying to train it to get better. You see a curve like this getting better and better. Hopefully it's not too jittery. If it is, you make some adjustments. But then you're trying to learn very, very complicated patterns about where these words go in space and how the adjusting based on different concepts in the transformer architecture. Okay. So anyway, this is a hands-on introduction. This is what neural networks really look like. This is how you train them. And this is what's going on under the hood when they're building these models. Okay, cool. Any questions? Yeah.
Is there any science at all into figuring out how many layers and how deep the layers are, or is it strictly just, it seems to always be a guess?
It's a guess.
Really?
It's an informed guess based on experience. I mean, people have scaling laws. They have ideas that if I make it this much bigger, then my loss goes down. I see this kind of performance. Maybe it's worth sort of saying like how you evaluate these things, right? And so, so language models, sometimes they have this picture of a language model, which is like, this is what it really looks like. This is back from when GPT-3 was around, right? It's kind of like some, I think it's called like a Shagath or a Shalabeth. It's a mythical figure, right? It's kind of like, looks like some crazy thing, who knows? But then you kind of like make it look like a person. You put a face on it so it like impersonates a person, right? Or impersonates text. And it's a very complicated thing. So right now, I mean, in terms of the way these things are trained, they're just big versions of the transformer model, and people know that you get certain performance for this and that, and you can scale up to different numbers of parameters. They look at other people who've written papers. Usually people will read papers. I mean, it used to be, before papers were generated by AI, people would just read the papers, and they would say, okay, well, the paper gives me good information. I'll try to implement that. And so general research sharing of ideas. Now I think it's more gated because it's not quite clear exactly what, what's real in terms of research. But there's a lot of internal research that goes into running a bunch of things, just like we did before, and sort of seeing what works. So it doesn't work, I need to increase the number of parameters. Okay, I need to sort of try this other architecture. And eventually things work, and you mine a vein that you've already gone down. So people don't usually try something very, very different. If you want to build something that works, you take what worked before and you tweak it a little bit.
But do you think the reason that someone can't come up with an algorithm to pick the optimal dimensionality of this is because of the nonlinearities of this whole problem to begin with?
Well, I mean, I can't say that they can't, and I know for sure that they have models that are trying to predict what size neural networks we should do to make the models, right? And so all of these questions that you're like, oh, I have a human decide, there are models that are trained to try to do that thing. And so it's not like people are just guessing blindly, but people also don't really know.
It's a neural net trying to design another neural net.
I'm sure that's what's happening. Yeah, certainly heard the industry talk about that. Yes, exactly. Exactly. How to improve the self-improve. Exactly. Okay, so the last thing I want to talk about is maybe just a little bit about how you run models locally, give you sort of a sense if you want to do this for yourself. Okay, there are lots of different tools out there. How many people have run their own model? Okay, a few people. Okay, so there are tools out there that are really easy to do. LM Studio is kind of a pretty easy one. It's sort of just an interface you can download for your computer. It'll run some of these smaller models on the order of, I would say, 3 to 7 billion parameters. Is pretty easy to run on your laptop. Larger models you can certainly run depending on your RAM available. If you don't have that much RAM, you can usually what they do is the idea of quantizing a model where to use it represent a number. They won't use all 8 bits of a number or all 16 bits of a floating point. They'll use only 8 bits or 4 bits or 3 bits or 2 bits, depending on how desperate you are to be able to run the model on your machine. And it loses some quality, but it still kind of runs, okay, and it runs faster. And so as a practical consideration, you can actually run reasonable sized models that do interesting things locally if you care about privacy or studying the model or repeatability, for instance, and not having random outputs. So that's kind of an idea. And then there are different backends as well. It is very, very well tooled, this space. So if you're interested in that kind of stuff, there's some links here. Okay. This is LM Studio. It's one of the ones that if I'm doing a demo, I would use. It's also Ollama, which is a very popular one. You can set up a model running on your computer, and you can send text to it and then get experiments back. So if you're a researcher, using Ollama or setting up an endpoint locally is a common thing to do. Okay. Have people heard of Hugging Face? Okay. Hugging Face is just the greatest, okay? And their icon represents this. Hugging Face, if you care about models and you want to know kind of what's out there, and I might flip to the internet to take a look if you want. This is the place. This is the GitHub of models. Okay, it's the one-stop shop for any open source model that's available. It has things to evaluate different models to know what models perform better than others, called leaderboards. It has a model card, like a little web page for each model to explain how it runs. It also can do some inference if you want to pay them to run a computer. On the back end, it'll serve a model for you, although it can be expensive. Okay, so Hugging Face has different models listed, each with their own model card. Usually it shows how the model performs. It has a little bit about what information is available. This is the Llama 3.370 billion parameter instruct model. So usually it's the name of the model, then the size, meaning the number of parameters, and then maybe some additional tuning that's done on it. In this case, it's an instruct tuning on top of Llama 3.3. Okay, 70 billion is a bit of a beast to run locally, but if you have like a Mac Studio, for instance, the memory could certainly accommodate that kind of a thing. This is also really interesting to know, how do you know what model to choose? There's an ecosystem of all these models out there. Once you get past the Claude or ChatGPT and you want to run your own, right, there's all these things that have been thrown out over the years, and some are still getting smaller. Some people want to make really small models that do well, as well as they can for being a small model. Like, I mean, if you want somebody to say what email is important on your laptop, right, you don't need the ChatGPT. You just need something that can read an email and be like, okay, it says urgent. Okay, this person's tone seems pressing, right? You want something that kind of like gives sort of a quick evaluation. So part of the field is moving to smaller models as well. But to know how well they do at different tasks, nobody knows until they try. Okay, so just like we talked about before. Yeah.
So if you can run a fairly big model on a souped-up home computer,
yep.
These data centers that they're building are unbelievably massive. And my question is that because there's just millions of people trying to do the same thing at the same time? Or is it they're building them so big because they can run models that you can't even imagine running on a home computer?
Yeah, you can't imagine running ChatGPT on your home computer.
Okay.
No one's going to run a trillion parameter model.
Okay.
Period. Even when they run it, they fragment it across many computers, and it puts the results together. So part of the model is here, part is there.
At that one data center, and yet you got a million people trying to do the same thing. Got it.
Exactly, exactly. So some of it is that computers only have so much memory, and you've got to fit the model into your memory to do the work. And so if your model is bigger than your memory on your particular computer, then you have to start getting really creative on the data architecture side. How do I get this model to be split over 5 computers, but they all talk to each other so fast that they feel like one computer? or this is training this part of the model, this side of the weights, this is training that side of the weights, and they feed together. So if you want to understand how good a model is at a particular task, you have to try it. Okay? And to try it takes some effort. And so what people have come up with as kind of the metric for how good a model is for any given area you care about, whether it's math or grammar or geography or looking things up or doing inference on spreadsheets, whatever it is, people have made a data set that evaluates that. Okay, and so what the data set is, it's called an eval. Okay, but it's basically questions that we fed into the model and then allowable answers. Okay, and depending on a metric to sort of say how good the answer is based on what the correct answer is. So maybe let's say capitals of different cities, and the capital is only one answer, and so it looks for that answer. Sometimes it'll say maybe it's an empathy test, and you'll want to know how do you rate sort of how distressed this person is, and there could be 5 categories, and they've got to get it right? And so you tell the model you can only choose from these 5 categories. And so whatever your model is trying to do, each skill is its own thing. You don't know if your model knows how to do it. Okay, and so every model that comes out gets run across all these different standard evals, and it gets a score compared to all the other models. Okay? And that's kind of how you can tell the latest and greatest for whatever you care about doing. Okay? These are all on Hugging Face. It's called, and this is for the open language models. And this is the leaderboard for that. Okay. There's also places where people can judge. Is this answer better than that? Sometimes ChatGPT will do that. It'll give you sort of 2 choices and say which is better. Okay. It's using that as preference data to train its next model. Okay. That's the idea. Okay. And also you can have things that embed text better or worse, and so those text embeddings themselves have a leaderboard. Okay. So the last thing I want to talk about, just to give you sort of a sense of how I've told you about what language models are. Hopefully you feel like I've opened the box a little bit, showed you the main ideas, the embeddings and the transformers and the tokenization. Okay. In terms of how an actual model works, though, it's pretty opaque generally. Okay. So even open source models are not always that open. Of the open source models that are out there, people have maybe heard of Llama, the Llama models. Llama 4 came out recently in the fall. DeepSeek and Quen came out a while ago, but they've been iterating as well. And there's one maybe you haven't heard of called Olmo, which doesn't get a lot of press, but that model actually turns out to be completely open source in the sense that they'll tell you the training data, they'll tell you how they trained it, they'll tell you the algorithms, they'll tell you the architecture, and they'll tell you the weights, meaning the actual model. Okay, and so I thought it may be kind of fun to talk about that as an example, so you can really see what goes into making a model, and then I'll be done. That sound okay? All right. So it has a tokenization scheme. If I can read this very well, put my glasses on. But basically, it has a vocabulary of about 100,000 tokens. Okay. It has a certain kind of tokenizer where it takes things and it conglomerates tokens until they get complicated enough that you're like, okay, I want to stop. Okay. It does some things inside there where it will mask. It'll have tokens for things we don't want to train the model on, like your phone number or your home address. Right, for people who are like mentioned in documents, you might want the models to keep some of that kind of stuff private. But that's kind of the idea, and it's kind of evolved over time what the vocabulary is. It started out with kind of a GPT-like 50,000 word vocabulary. Now it's about 100,000. Okay, and so the average compression is about 3.5 characters per token. So that tells you how words go or characters go into tokens. Okay. In terms of the parameters in the model, this is a 7 billion parameter model. It's also a 35 billion parameter model. Okay. For this model, it has most of the parameters are in these like internal feed-forward neural networks. Okay. About 2/3 of it. 1/3 of the parameters are in the attention vectors, how things modify other things. Okay. The embeddings themselves, where they start out, where the words go in space, only takes up about 6% of the model. Okay, so most of the space is not taken up by something else. The space this lives in is 4,000 dimensional. So you can imagine to embed all the tokens into this space. I have 100,000. I have a matrix that goes 100,000 rows, 100,000 possibilities, and then each of the columns for that, or that's how you want to say it, but each of those gets 4,000 embeddings. Okay, so that turns into about 400 million parameters just to put the tokens in space. Okay. Then on top of that, the model is rejiggering how tokens affect other tokens depending on the concepts, okay, to be able to do things. Cool. The training data that goes into this, there's a thing called a common crawl data set, which is what you might think of as like I scoured the internet and took stuff, okay, like what's the basic internet information. Okay, so that includes things like Wikipedia, for instance, right, a bunch of public repos, things like that. There's code specifically from GitHub. There's a bunch of papers that come from science. like the archive, things like that, online math problems, online encyclopedia references, and then a bunch of books. Okay? And that's what they fed into this model to train it. Okay? So it's read all of that. Okay? It's all been part of the training data. It's what's used to adjust itself to make itself better. Okay? If you care specifically about the details, I put a slide here together, but just to give you sort of a sense, there's about 9 trillion tokens that go into training this model. Okay? So it's a substantial amount of data that this model has read. Okay? Certainly read more than you or me. Right? And so in some sense, it's kind of amazing that these models can read all this stuff and kind of learn. Doesn't mean that you can recall everything. And at different stages of the training, it gets fed different things. So at the beginning, kind of like when you're teaching kids something, you might not give them like your advanced science book in kindergarten or first grade or fifth grade. You might wait till they're in like 10th grade or 12th grade, right? And same thing with models. They kind of can't understand complicated things until they can understand simple things. And so there's kind of this layered training that goes to making a model. So it starts out with sort of simpler things, then it turns into sort of longer, more technical things, and then finally at the end, it's sort of behavioral things you want to train it on, so it can sort of interact with you in a nice way. Okay. In terms of actually training the model, the amount of time it took to do this for the initial training was about 25 days. Okay, so about 3 weeks roughly. Okay. After that, there was a little bit more training. Took a couple more days, and then finally at the end, there's a little bit of like making it look nice, okay, polishing the model. Okay, the sort of fine tuning at the end. Okay. And that's kind of the idea behind this. A lot of compute goes into this. Okay, it says 87 million GPU hours. Okay, depends how you count that, but that's a reasonable amount of compute. Okay. And that's kind of generally what I wanted to say about language models. If you want to make them even better, there are things you can do. You can try to put better prompts into it, ask better questions, ask more specific questions, more precise things, tell it to tell the truth, tell it to say when it doesn't know what it's doing, things like that. You can give it specific bits of data that are relevant to your question, like look it up in a database called retrieval augmented generation. Or you could try to chain models together in different ways called agentic workflows, where models can decide what other things to do next and give them different tools. So that's kind of what people do nowadays. People used to more focus on the models themselves, and so that would be kind of more about fine-tuning the model, meaning training it a little bit afterwards, maybe put some extra weights on and let those move around, or do additional training with actual data of your own. Okay? So roughly, this is kind of the broad view, opening the hood and giving you kind of an overview of one level deeper into sort of what language models are. Hopefully it's a reasonable introduction. Thank you for staying, and if you have any questions, would love to chat more. Thank you. Question over there first. Yeah.
As far as agentic models, as I understand it, and I would love for you to tell me if I'm wrong, rather than next token prediction, it is predicting the next proper action. And then within each step is an LLM doing the task. Is that correct?
So it depends how you think about it. So what agents do, and there's a couple different things you call an agent, but one of the sort of main things that you can do is to give models the ability to use tools. Okay, so that could be call a web page, write to a file, read something, do a search, things like that. And the ability to use a tool is something a language model will decide whether it wants to use, but that'll be part of the tokenization scheme. So it might say, well, tell me what tools I have available. That's how you sort of start the model. And then it will say, okay, well, if I need to use that tool, I'll decide to try to use that tool if you give it the syntax for that. But it's not built into the model generally. It depends how you do it. But when tools first came out, they were part of the training. They were part of the prompting of the model, not the training. Yeah. And so the model itself is still producing tokens. The language model is still producing tokens. But one of those tokens is use a tool. And as soon as it sees use a tool, then the operating system will come in and then take that instruction that says, tell this to the tool. It will go off, tell that to the tool will run. It'll take the output of that as a separate process and then bring it back to the model and put it in the context.
Then what does training data look like for dynamic action? Because you can scrape a web page and that's all text. But how do you show a workflow in multiple steps across multiple applications, terminal, new tabs, whatever it is?
Yeah, that's not part of the LLM itself. That's part of the infrastructure around it. So the infrastructure will say, well, and I taught a class about this, and we use N8N, which is a nice graphical tool that you can sort of say, run this question with this language model, and then when it finishes, pass it to this other thing, and then run the script and sort it, and then tell this language model to evaluate how good that answer was, right? And so you can have workflows that happen around language models, this overall tooling, which could be tools that it calls, but also an infrastructure about how language models themselves are prompted. But that's not part of the language model itself, that's part of the agentic framework around it. Does that answer your question?
Kind of, I'll look into it further. But my last question is, do you do any like workshops on the different structures of models? Like, I'd like to know more about CNNs and RNNs.
We have, I guess maybe John Halverson is the person to ask about that. Research Computing has, during winter session and then during the year, different workshops. I think in January, Julian and I did a workshop on exactly that, different types of data science models, and it was a 4-day workshop. I think, certainly the GitHubs are online. Is there video as well? No, there's no video. Okay, so there's some repos we could show you, but Research Computing is always doing trainings like that, so we'd love to chat about it more. Sure.
The question is, search engine has been, many years, right? And then after that, we have the Google announced transformer architecture in 2017, combined with NVIDIA's GPU, TPU now, and then a lot of parallelism, is getting to this new design of AI. Now the question is, the large language model produce the meaning of your inquiry, and then the backend to search for the result of the internet. Is that remain the same technology as the many years ago Google search engine, that type of things, or things are different now?
Yeah, I mean, it's hard to know because it's proprietary, but PageRank started out as one algorithm. It has evolved over time. It was originally a paper, a public algorithm as to how it works based on link frequency and things like that. It's been people have been trying. It's like cat and mouse game about search engine rankings and what do you do to sort of keep things correct or mitigate that type of stuff. AI is being layered into that process, but I can't really comment about what search is now. I don't really know, but I think fundamentally it's the same. But then there's an AI layer on top of it. That'd be my guess, but I don't really know.
Okay.
Yeah. Yeah, question.
Yeah, thank you for the great talk. I was just wondering, so what is often employed in these models now as well is this post-training stage where they use a lot of reinforcement learning. And I guess also to the question that came up earlier, I think that's probably the source that has been attributed to these large jumps in recent years. And I was wondering, the example you made regarding Almo, I was wondering, do they disclose anything about their post-training process?
Yeah, completely transparent. Yeah, so you can look at their website and you can see you could train the model if you wanted to. Yeah.
And do they do anything besides like RLHF? Do they have any of these new like verifier-based reinforcement learning pipelines?
I'm not sure. I haven't looked at it carefully, but I know that it's all out there on the website. They have a GitHub.
Okay.
So yeah, they do RLHF, but that's all I know. I didn't look at it carefully enough before. I just wanted to give kind of an example of if you want to take a look, here's where it is.
No, yeah, of course, that makes sense. Thanks.
Sure.
So thanks. You mentioned the idea of a context window, the sort of the maximum amount of tokens that it can take in a given chat. What happens if I keep chatting with it and it sort of just runs out of the context window? Does it like stop referencing something? Is it still referencing parts of the previous chats? And also, if I feed it with like a paper, like a 30-page paper, is it reading the whole thing if it's sort of out of its maximum context window, or is it it's not telling me the truth that it really read the paper?
It's hard for me to know what it's doing because it's not transparent. That's part of the UI layer as to how it decides to feed things in. I know, for instance, Claude Code, when you're using it, it will actually run out of context. It'll say this percentage left, and then it will kind of reboot, transparently to you. Like, okay, well, you control the context. But I haven't had too much where it's run out of context when I'm doing a session, right, during a chat session. It could be because I didn't put enough into it or not. So I don't know. Everyone will sort of handle it differently. There are things that try to sort of boost the context, different ways to compress things that try to keep track of the context as part of the one strategy. There's also sort of longer context type of mechanisms to increase the context length of a model, even though it has a certain window in terms of encoding and compressing things. But I don't really know what it's doing underneath. But I can tell you every model does have a fixed context window, and they advertise what it is. So I think the latest Claude Opus is about 1 million tokens. And you can look at the blog posts. They've got great blog posts about it. Yeah. Yeah.
So you referenced in a few slides back all the different models. Some are better than others. One was geography, mathematics, and so forth. You hear a lot of stuff in the news about AGI, and it seems implausible to me that they're going to get there with the current technology of you would have to string together an infinite number of models. So my question to you is, in your opinion and your knowledge of the field, is what we got right now ever going to get to it, or there's got to be a new breakthrough somewhere?
Yeah, these are questions that are really impossible to answer, just so people know. I mean, what does AGI mean? Everybody has their own idea of what AGI is, artificial general intelligence. I take that to mean, can there be a model that's smarter than the smartest expert on the planet at everything, at anything, right? At everything, right? So it's a sort of superhuman in the sort of max sense of any question you might want to get answered. Some people say that we've already achieved it. Some people say that we haven't. I think that my personal opinion is that there will be a point where models can do everything that we can do because we're telling them how to do it, right? And they are infinitely scalable in this sense. You know, it's very easy to be able to have them be bigger and better. And you see the improvements that have happened in the last couple of years. I don't see a natural plateau to that. And so I think it's entirely reasonable, but does that mean they'll know everything? No. Will they be able to research any topic and instantly know the answer? No. And so, you know, as a milestone, it's kind of like a science fiction milestone because already they can do a lot of things much more efficiently than we can do, right? And when we can use them, it's to our benefit to do so. At some point, they might do everything better than we can do it, but we'll still be here. We'll still be using them for something, and we'll decide what we want to do with our time in that window, and whether they, you know, can do better than the biggest experts in the world. I don't think that's really a meaningful notion. I think it's much more meaningful, like, can they be used to do productive work for most things we care about? And that's not as sexy of a thing to talk about, but I think that's kind of the place that agents now are trying to sort of start to understand that ground. Like, what are the things that you do in your daily life can models really do for you reliably? So I asked at the beginning, you know, how many people use it for something important? Very few people raise their hand, but I think in the not too distant future, the next couple of years, everyone will raise their hand, and they'll be doing everything from, you know, home automation to things with your car and things with your, you know, your schedule. Everyone will have a personal planner. There's lots of things that are kind of like low-hanging fruit for, like, gosh, that's not that hard. I wish I had a model that was trained to do it, and so I see the natural space there.
So all these models were based on basically from humanity. And are these models now at a point where they're doing things that are beyond us? That, like, are they solving problems that no human has done yet?
Well, language models are one particular type of model, like I said. So for example, there's this, and people have heard of AlphaFold. Okay, so AlphaFold is a model that tries to predict from proteins from a sequence of DNA or RNA. How does protein, so from that sequence, fold, right? What's its physical configuration? And that's a super hard problem. I knew people when I was in graduate school in the 90s who were working. That was their whole PhD, was trying to understand a little piece of that. And now basically it's a solved problem. And the person who worked on it was a DeepMind, along with some other chemists. They won a Nobel Prize recently for this. And so that's an example of something that we couldn't do. And we worked really hard to make a model, and now it does it pretty reliably. And so yes, it's certainly happening in specialized areas. What we've seen before, like chess, right? Chess went to Kasparov, lost chess to Deep Blue, and all of a sudden chess fell. Go fell, right? When recently, Lee Sedol. And so each of the specialized applications, people make certain models to do that thing. And you know, chess players don't train with other chess masters anymore. They train with the models to learn how to do, because they're the best at that thing, right? And so,
let me ask my question in a different way. When we use these tools, we typically ask the models a question.
Yeah.
You know, how to do this, explain something.
Yeah.
Are they at a point where they're actually able to create their own questions?
I mean, oftentimes when you're talking to Claude, it'll say, you know, here's your question, what about this? Or do you mean that? Or I think so the answer is yes. It certainly gives context and prompts to you to sort of get an idea of what you mean. But we can talk more afterwards. Yeah. Awesome. I think we're at time now. So thank you everyone for coming. I hope the food was good. And if you have any questions, happy to chat. Thank you.